Welcome, everybody. So today we are lucky to have Lobo joining us from UC Irvine. And it did her PhD wrapped up in 2021 at Caltech. If you hear Anna tell it, Anna's PhD was in circulation dynamics of ocean worlds, but I feel like that really undersells the fact that Anna was able to span icy worlds in the solar system and oceans underneath icy crusts in the solar system and dynamical work there, as well as dynamical work as applied to Earth-like exoplanets. Anna is now doing a postdoc at Irvine, and so is going to be telling us about some of her postdoctoral work, which is on atmospheric dynamics of exoplanets. I think emphasizing faint stars. Are we going to get into K-dwarfs today?
If we have time, yeah.
Okay, we might make it out of the M's and into the K's today.
Well, thank you everyone for coming. So yes, I was saying we're going to be talking about exoplanets, focusing on M-dwarf exoplanets, but I thought we'd start with a little bit of a broader view and work our way there, and hopefully if we have time at the end we'll get to the K's, which is a bit of a new project for us as well. And so yeah, I started my graduate work thinking about potentially habitable planets. And so I came up with a very convenient umbrella term of water worlds, which was starting to be used at the time, and it worked out very well for me because it encompassed everything from the icy moons in our solar system to exoplanets that could have water. And the reason I like this term is because it draws attention to the one key ingredient that I personally care about, which is water. Water is the minimum for life as we know it, and so the search for a planet that can is very much tied to the search for a planet that could potentially be habitable. For me, the interest there is in what are the climate conditions, what climate we might find, trying to understand what these worlds could look like. But today we're going to be focusing on things that look more like Earth, so Earth-like exoplanets, as close to Earth as we can get in these regimes. There's a couple of reasons for this. I come from more of an earth science background, and so I like to approach earth science, planetary science from that foundation in Earth's climate sciences. Earth is our best understood water world. Our understanding of Earth is based on a wide range of data sets that we will never have for planetary sciences. We can glimpse into Earth's past using things like ice cores and tree rings and try to understand Earth's climate evolution. As an astronomer, it's so easy to take for granted our foundations of climate sciences, but just go ask an Earth scientist what will Earth look like in 1,000 years, and you can try to remember that this is very much a field in progress. And so I like to work at this intersection where we can also make a few exchanges between planetary and Earth sciences as well. I also like to show the slide, if nothing else, for the instrumented seal. All right, so we're going to be talking about Earth-like planets. I started this work actually with what I classify as like Earth analog studies. So those studies where you take Earth, but you tweak something. These are very famous for rotation rate experiments, for example. What happens if you take Earth, spin it a little faster, slow it down? Do we understand how the dynamics change? Does it make sense with our foundation of climate dynamics? Or potentially even more well-known, the experiments of if I take Earth and I scooch it a little closer to the sun, or put it a little bit further, does my understanding of climate remain sound? By the time I started my PhD, what I wanted to do is take this and explore parts that had not been done yet. What happens if we take Earth and we tilt it a little bit? This is interesting from an Earth climate point of view, because it allows you to disentangle thermodynamic and dynamic constraints. All of a sudden, most of your energy is being put into the poles instead of the equator. How does the atmosphere respond? And so that's sort of the Earth side of the question. From a planetary point of view, the question was, how do seasonal cycles work on more extreme exoplanets? What kind of seasonal phenomena should we expect? How does that temporal variability potentially impact our ability to diagnose this planet's climate? So that gives you a sense of sort of the dual nature that you can achieve with these Earth analog studies. And I want to highlight just one result from this work to sort of ease our way into the exoplanet discussion. And so here I'm showing you Earth-like on the left and high obliquity on the right. And you're watching the insolation move. We're going into southern hemisphere summer now, back to summer. And following the same seasonal cycle, here's a vertical profile of the water vapor. So first glance, it should maybe be intuitive. Water vapor is following the seasonal cycle, more water vapor when it's warmer. There is a higher peak of water vapor in the high obliquity case. It's also shifting to the poles. So while for Earth, the concentration is higher in the mid and exotropics, for high obliquity, you get your summer peaks right at the high latitude. So pretty intuitive. But if you watch it just closely enough, you'll notice that the water vapor lags the insolation. So it's not huge here, but it's about 2-3 months, which matches with Earth's climate inertia. It would be longer if the planet had a larger climate inertia, or shorter, depending on the setup. But for Earth, it's about 2-3 months. And this is something quite curious of a feature. So while for Earth's atmosphere, a lot of this water vapor just gets shuffled around over the seasonal cycle, for the high obliquity case, this water vapor is evaporating and condensing locally because it's happening in the really high latitudes where the atmospheric circulation isn't as intense. And so every summer, you evaporate a ton of water. Every winter, it condenses and precipitates out locally, and just a small fraction gets ejected. And evaporating and condensing water is a huge energy source and sink. So every summer, you have a surplus of radiation. A lot of that surplus goes into evaporating that water locally. And so this temperature is not going to rise as much. Some of that energy is now going into the water. And as the radiation disappears in the winter, it gets dark, it gets cold, but you're going to start condensing out water and releasing latent heat. So it's not going to get as cold. And here's where that delay comes in. It's happening on about a 2-month delay relative to the radiation. So you now have a heat source in your pole during winter. And that's enough to actually keep the pole a little bit warmer than the mid-latitudes. And it's enough to shift the polar winter by about 2 months. Now, this may seem mild in terms of astronomy numbers, but in terms of atmospheric dynamics, temperature gradients are critical. So while this would be our typical winter on Earth, somewhat simplified here, I'm just showing you the Hadley cell, the Ferrel cell that form. The summer cell is so weak that it's not showing up here with these contours. When we run our high obliquity case during winter solstice, those temperature gradients are just strong enough that they actually remove all of the baroclinicity that you need to form the Ferrel cell, and so it disappears. You get a wider Hadley cell, which is naturally expected. It's always a little bit wider, but Ferrel cell disappears, storm tracks disappear, your eddies disappear. And we were fascinated by this in the beginning of why does this happen? You have this huge energy imbalance at the poles, and all of a sudden your Ferrel cell's gone, your Hadley cell doesn't quite make it to the poles, and the answer was that water vapor lag. And so rather than take you through all of the derivations, if you like looking through moisture budgets and energy budgets, it's all in the paper, feel free to have fun. But just to sort of prove this to you, I'll show you the same simulation without water vapor, and you recover your Ferrel cell, and the Hadley cell goes back to a little bit closer to its original size. Still broader, but a little bit more similar. Talking about Ferrel cells, especially to astronomers, it's very abstract. But I like to start with this result. Just hopefully you can appreciate by looking at the dry high obliquity case and the low obliquity case, the power of water here. But this is enough to make your dynamics actually start to look like a low obliquity case. And it'll matter more for every single planet we're going to discuss for the rest of this talk. I'll tell you why in a minute. But this is one of the first times that I stopped in my PhD to really appreciate that water isn't just the end goal, but it's a critical question when you begin your simulation. We have to be very cautious about how much water we add to the system, where we put it, and what assumptions we make about it. It's not just something we can hunt for. So that being said, I promised exoplanets, and that is what we will now switch over to. I'm sure you're all very tired of all of the exoplanets we have discovered so far. Here we have planetary mass by orbital period. As someone who wants to find another Earth, a convenient thing would be to look for an Earth-like planet around a sun-like star. That is not currently a very achievable goal. Oops, quick one. So I'm sure I don't need to reiterate this, particularly for this department, but it's a bit of a hard sell right now to go looking for Earth clones. So I want to stay close to Earth as possible. So I've chosen to focus for the last few years on rocky planets around dimmer stars. You'll notice these are marked in orange and red. That is not a coincidence. These are M and K-dwarf stars, planets orbiting in K-dwarf stars. many advantages to studying M and K-dwarf planets, particularly M. They are the vast bulk of stars that we have out there, 76% of main sequence stars. They are longer lived, so that gives you more time for life to potentially evolve. Because they are dimmer, because they're smaller and dimmer, it's a lot easier to find their planets. A lot of reasons for us to do so. For me in particular, I want to find planets in the habitable zone. Since their habitable zone is much closer to the host star, it is also much more accessible to us right now. So for a sense of scale, a planet receiving Earth-like insolation rates at 1 AU around the sun, for 80 Leo, which is the star we're going to focus on today, that would be 0.15 AU. So that's much closer to the star than Mercury is to the sun. Awesome. So we want to take Earth, we want to put it around an M-dwarf. What is the minimum we have to change? Well, it's very close to the host star. Gravitational forces are going to be wild. We have to assume that this planet is going to be tidally locked very rapidly, and many, if not most, will be in synchronous rotation. So that means permanent dayside, permanent nightside. That does not mean zero rotation. So from a dynamics point of view, that is important to remember. It just means the rotation matches orbital period. So you still have a Coriolis force, but you do have permanent dayside, permanent nightside that will be a key to understanding its climate. Just to give you a cartoon for some of the things we'll be talking about today, if we imagine we have a dayside and a nightside on this planet in sort of a simplified box model, dayside has incoming stellar radiation and outgoing thermal emissions. Nightside only has outgoing thermal emissions. In order for this to ever reach steady state, you need to have convection, you need energy transport. That transport has two possible modes, atmosphere and ocean. We are today only going to talk about the atmosphere. This is for several reasons. One, convenience, but two, several studies have shown that ocean circulations in planets will be weaker, so the energy transport would not be as important. And lastly, as we'll get through this talk, we do have to question whether or not we're going to find global interconnected oceans on these planets that would be needed for the ocean to contribute to the energy budget. So for now, we're going to be talking about the atmosphere, and we'll get to that as we get through the talk. Great. So we have our Earth orbiting an M-dwarf. It's accessible. We can find it. We can see it. We made it tidally locked to account for the gravitational forces. What else do we have to do? It's no longer orbiting a sun-like star. You're now orbiting a redder star. Redder means a lot of near-infrared radiation. So here you have the stellar wavelengths. I put two different M-dwarfs there in red. This is going to affect pretty much every climate feedback that is important to understanding Earth. For example, ice albedo feedback, which is the basics for understanding Milankovitch cycles on Earth, becomes much weaker around an M-dwarf. Because actually snow and ice albedos, which if you look here, this is about 1. In other words, they reflect almost all visible light. It's not as high as you get to longer wavelengths. So ice and snow don't reflect that much near infrared radiation. So when you're orbiting the sun, your peak is invisible, you're reflecting a lot of that light. When you're orbiting an M-dwarf, you're not reflecting quite as much. So your albedo is going to drop by about 50%. So it still matters, but it's a much weaker feedback. In contrast, your water vapor is going to become very finicky. So if you think about how we think on Earth about our greenhouse gases, and in particular water vapor, Earth's peak insolation is invisible. There's not a whole lot of absorption there. For a cartoon version of Earth, you can think of it as being transparent to incoming radiation. And then when the Earth has thermal emissions, those are going to start interacting and absorbing over in the longer wavelengths where there's actually significant water vapor absorption. For an M-dwarf, that peak overlaps with a decent number of absorption lines. So this means that your atmosphere is absorbing both incoming and outgoing radiation. So you have to be very careful about how we interpret the role of water vapor in these atmospheres. Now, these aren't the only climate feedbacks, but they're the ones that are most relevant to us today. But pretty much every time you change the surface for one of these planets, you're going to have to go back and see how much it'll impact your results. We want to give a more tangible example. So let's start with our Earth-like case, or an astronomer's version of it. This is run with the ExoCam model, which is an adaptation of the CSM climate model, one of the big clunky CMIP5 Earth models. But we run it in a simplified configuration, slab ocean everywhere. So very simplified version of Earth. We put it at 0.154 AU so that it's receiving the same total amount of energy as Earth does, but it's synchronously rotating for 80 Leo, that is a 34-day orbital period, and everything else is kept as Earth-like as we can. And you get the temperatures seen here on the right. In this projection, the substellar point is right here at the center. So the dayside temperatures, I know it's a really large temperature gradient there because we're going to be comparing a lot of simulations. The dayside temperature is a nice 15 Celsius, a little bit cooler than your Arizona day. Nightside is all below freezing. And throughout the talk, I added the black hash marks for anything between 0 and 50 Celsius to be a sort of hand wavy region of interest for potential habitability. So let's take a look at our M-dwarf Earth. One very frequent result that has been shown with a variety of models for an aquaplanet orbiting an M-dwarf is that it is cloudy. Very, very cloudy. Here you have these contours in blue. Dayside cloud coverage is basically 100%. That means you have a high top of atmosphere albedo that's shown in the color contours there on the dayside. So a chunk of your radiation is going to bounce right off. But whatever radiation does make it through, if you look at the plot on the right here, is going to get heavily absorbed. So right at the top of the atmosphere, you're going to see a lot of absorption taking place. And sorry, my view here. But as we make our way through, wherever you have high peaks of water vapor in the atmosphere, that radiation is going to get absorbed. And so if you look at the net stellar radiation making its way down over here on the left, you'll actually notice by the time you get to the surface, and this is at the substellar point, so where you think of as like the center of your dayside, there's hardly any radiation making its way to the surface. This is about 50 watts per meter squared. That's like really dark sunset shifted into the near infrared. So like to us, it would be pitch black at the substellar point on this planet. So something interesting to keep in mind, it doesn't preclude habitability, but it definitely does maybe change what we would expect to find. And so rather than imagining a planet like this, if you want to have a picture in your mind, maybe a little bit closer to this. But this is our Earth-like case. This is sort of a random planet we picked just to get as close as we can. And this climate regime has become somewhat known as the eyeball planet. I think the artistic representation explains why. Let's go ahead and look a little bit more broadly at our habitable zone. What happens if we step in and out? A little bit further out into the habitable zone, if we go, our Earth-like case is in that 1400 watts per meter squared range. So if we go out to 1100, we get very low dayside temperatures, a frozen nightside. A little bit warmer, we end up here with the nightside starting to melt, and then eventually a runaway planet. So before going too much in depth, I want to take a look at the atmosphere of these planets and some of the basic dynamics that are taking place. So just bear with me to go into the weeds just for a little bit. I want to show you the radiation budget first. So here we've taken a cross section from the substellar point to the interstellar point. So yellow is our incoming radiation. And then if we remove the top of atmosphere albedo, you get the dashed line. So you can kind of just focus on the dashed line since anything that bounces right off the top doesn't matter to us. And red is the thermal emission. So comparing just our warm planet to our Earth-like planet, you notice that the thermal emission doesn't change very much. So these are very cloudy, very optically thick dayside atmospheres. They struggle to increase their emissions. It doesn't change an awful lot as we shift in, whereas, of course, your incoming radiation is changing. So if you think of it in terms of an energy imbalance between what's coming in and what's going out, you remember that cartoon from the beginning, you'll notice that the imbalance is increasing. So our warmer planet has a greater energy surplus on the dayside, deficit on the night side. So naively looking at this, we might expect that this means an atmosphere is going to be more dynamic. You're going to get stronger winds or something to make up for this increasingly imbalanced radiation budget. Turns out that's not the case. This is a fun little work to keep in mind, that our warmer planets actually end up having a weaker overturning circulation. So these are stream functions. You can actually think about it like the Habitable cell plots from earlier. So I've added the arrows so you can see the direction of the flow. Where the substellar point is here, you get ascending air, you get a higher level flow upper branch descending as it cools off and then converging again at the substellar point. And you'll notice that our colder planet actually has a stronger overturning circulation. So this is probably a bit counterintuitive, but the explanation is in our Hadley cell. So I'll get to that in a minute. But I like to point this out in part because in terms of racer mixing timescales, your overturning will matter. So your colder planet would actually be a better mixed atmosphere if you're thinking about short-lived chemicals. In terms of wind speeds as well, those would be higher in our colder planet, whereas our warmer planet is very subdued. And so how does that balance the energy budget? Well, same reason as our Hadley cell, the upper branch and the lower branch are competing in terms of energy transport. This happens on Earth. The upper branch of the Hadley cell competes with the lower branch, and only the cancellation matters. And that's exactly the same thing that's happening here. So this is a plot of the energy budget, where I'm showing you the energy flux divergence. I know that's a mouthful, but you can think of it as if it's positive, you are exporting energy. And if it's negative, you are importing energy. And we're looking at the substellar point. So the upper atmosphere is exporting, the lower atmosphere is importing. Look at that curve. It's very similar. It's going to cancel out if you vertically integrate it. And I promise you don't have to get into the details here, other than I want to show you these totals at the bottom. This is the vertically integrated value. And all I want to show you is that this total over here is tiny. This cold atmosphere is incredibly inefficient. It's moving a lot of mass, but the total energy transport is very, very low. And our warmer planet, my mouse is lagging terribly, but over here, has a more efficient atmosphere. And so even though it's moving almost comparably almost no air compared to our cold case, it is a more efficient heat engine, to think of it sort of colloquially in that sense. And so the planet becomes more efficient, and it can keep, and it can match its energy budget without having to move quite as much air. So those were the weeds. I promise we will not quiz you on that later. But I wanted to show you this to introduce how we kind of started exploring these planets, because we wanted to see what climate regimes they could actually be in. And so if you look at aquaplanets, they have a very smooth transition. So you can look at the contour plots above, or you can just look at the scatter plot below here with the maximum and minimum temperatures as we move closer to the star on the left. You'll notice that the night side is warming up, dayside temperatures increase a little bit more slowly, but as you move in towards the planet as you move in closer to the star, the planet becomes more and more homogeneous. So well enough, that gives us our kind of standard climate regimes. You think about the outer habitable zone as a snowball planet, you're going to shift into the eyeball climate regime. That island of habitability is going to grow as you move inward. Great. Eventually, is this like the perfect planet that you manage to melt everywhere? So we'll discuss it, and you'll hit a runway if you go too close. Now, this is a very convenient picture, but I wouldn't be giving this talk if that were the end of the story. So time to break it apart. I started by saying we're going to be discussing water. So what is our assumption so far? Aquaplanet, let's tear into that. What happens if it's not? So what happens if we do the extreme opposite and go to Tatooine and we say it's sandy surface, we limit the amount of water. We did these simulations using the same climate model, but we prescribed, instead of an ocean, a Sahara-like surface, and we did different amounts of water vapor in the atmosphere. The one I'm going to show you today is very limited. So think about like a global Sahara or, Tatooine. That's convenient. Yes?
Can I just ask about the expected limits for being tidally locked around this? Where do you expect that to end? I was just surprised at how far out.
So for all of the simulations that I've shown today, you'd be looking at a tidal locking time scale on the order of hundreds of thousands of years. I think the longest one was 600,000. Of course, there's sort of mitigating factors that could prolong that, but all of them are in a pretty tight time scale. It's still they're all still pretty close into that, packed into that. Right, so we have our dry planet. First basic things that change. Oops, my key is sticking here. Before we talked about the effect of clouds. You took away the bulk of your water vapor, those clouds are going to decrease. So you are gonna not have as much cloud coverage. So there's less of an albedo right off the bat because you don't have that huge cloud deck. So there's actually a little bit more radiation entering the system, even if it's placed in the same orbit. You're gonna get less absorption in the upper atmosphere. So this means you no longer have that huge absorption that's gonna mess with your lapse rates at the top. So that's gonna facilitate a deeper circulation. You're also gonna get a lot more radiation reaching the surface. So you can see here, the radiation profile is a little bit more familiar to us. In a lot of ways, this planet is actually more intuitive to what we're used to for thinking about Earth. In terms of the atmospheric circulation, it looks a lot more like our cold planet than our hot planet. So these two are both in the Earth-like distance, for about 1400 watts per meter squared stellar constant, but you recuperate that very deep overturning circulation and moving a lot of mass. Talk about the radiation budget before, you'll notice that now your thermal profile has changed dramatically. So while the aquaplanet has a thermal emission minima on the day side, it switches to maxima for a land planet. You'll also notice that in terms of energy surplus and deficit, you're a little bit more balanced. You're a tiny bit closer to radiative equilibrium, even though you're not there. And so you have a little bit less energy transport technically being required. It also works out that this circulation is impressively inefficient. You can probably tell from the stream functions, it's a very intense overturning. It's a vertically very tall circulation. You have very large contrast between your sensible energy transport and your gravitational energy transport, and your total is tiny. So impressively inefficient atmospheric circulation. So this should highlight the indirect role of water vapor in your atmospheric dynamics. So you notice that the latent component, the role of water transport in the atmosphere, is pretty much negligible up here. You can hardly see the blue lines. So moving water doesn't directly impact the energy budget, but it affects it indirectly by changing the structure of the circulation. And because you now have this really inefficient atmospheric circulation, you can sustain huge temperature gradients between your dayside and your nightside on the same planet. So your dayside temperatures are going to rise up. So if we look at our Earth-like case over here, dayside maxima are much higher than for the aquaplanet. This is both due to changes in the atmospheric circulation and the fact that you have lower albedo. And your nightside temperatures are going to plummet because you're transporting very little energy over nightside as well. And so we see across the habitable zone for our land planets that for a large portion of that parameter space, you're going to have inhospitable dayside temperatures and frozen nightside temperatures. Your habitable zone is now shifted to somewhere in between. Largely near the terminator, or actually at the terminator, will be where you're going to get moderate temperatures on these planets. And hence the term terminator habitability. This was a quirky climate regime for us to find. It's actually one of the first that was predicted from science fiction. When people started talking about synchronously rotating planets, there's this idea that we'd eventually find planets with the terminator habitability configuration, but it hadn't popped up with climate models because we started off with aquaplanets in the early days of these studies. And so it only pops up when you start considering dry planets. And so this is fun to point out first that you can still have a habitable region, even if dayside temperatures have exceeded what we consider to be hospitable temperatures. So it's something to keep in mind in the hunt. But what I want to make the case for now is that these are actually appealing targets in their own right. So I'm going to tell you a little bit about these planets and then why we should expect them to be common. So first, a little bit of a fun tour of a terminator habitability land planet. As I mentioned before, they get a lot more radiation at their surface. So if we're hoping for synthesizing adjacent biosignatures, there could be some significant advantages here for a more Earth-like planetary climate. So here you have radiation reaching the surface compared with sort of habitable zone hash marks. I really just want to emphasize this, so I'll also show you a line plot, also with radiation reaching the surface. When the paper came out, a lot of people wanted to call it like the twilight zone, because we're talking about habitability near the terminator. And it's a fun name, but I think it gives people the wrong idea. So if you look here at the insolation values, even near the terminator, the land planet is always getting more insolation than the aquaplanet. So this is not darker than anything we could have conceived for an aquaplanet. So we're actually talking about environments that are receiving more light than the substellar point of an aquaplanet, or really any other portion of the equivalent aquaplanet. So these are not dim worlds in that sense. Sort of just a fun aside, but we often get asked about the winds, since we're talking about the intensity of the overturning. Since it's so much stronger for these land planets, does that mean that life would have to deal with hurricanes? And the answer is no. High altitude winds are stronger. So just like Earth has jet streams, these are very comparable to the intensities of Earth's jet streams. They're technically used as hurricane level winds, but surface winds for all of these tidally locked aquaplanet and land planets are very mild. So they all have breezy days, and the values decrease right around the terminator. So just a little bit of a fun aside, but you do not have to worry about hurricane wind speeds on these planets. Now, other advantages to land planets, they actually may be in the short term some of the better observational targets. So this is work that has been done by several other groups, and I'm going to borrow here TAD's 2020 figure just to make a quick point. As I showed before, land planets are going to have significantly less cloud coverage. For transits, that's going to give you a much greater transit depth. So here's a comparison of the same measurements taken with clouds, which are here are little bottom numbers, and without. And so I'm not going to linger because I'm sure there are people in this department who could go on and on about this a lot more than I can. But the point being that our water limited planets will be a whole lot easier to characterize, to identify their water than our aquaplanets. So in terms of what we can do in the near future, we may have some good chances here. I also really like to think about their thermal emission patterns being so distinct. So here's the thermal emissions for all of the planets we've been discussing today. I'm just gonna draw your attention to the two Earth-like cases. So the Earth-like aquaplanet and the Earth-like land planet. And you'll notice that, of course, they have opposing patterns. The aquaplanet has a minima when you're seeing the dayside, and the land planet has a maxima when you're seeing the dayside. But substantially much greater variability for your land planets overall. So you're looking at a change of about 400% from minima to maxima, and that delta is an order of magnitude greater for the land planet than the aquaplanet. It's also very closely tied to the surface temperatures that you're getting on that planet. So it might be a lot easier for us to derive information about the surface climate using a land planet's thermal emissions. And so this is something that we're trying to explore in greater detail. So we're very hopeful that land planets would be a plus, not a negative, if that's what we find around M-dwarfs. And I've sort of taken the backwards approach here, first getting you interested in them, to now make the case of why we expect them to find them. So, yay, they can be in a terminator habitability regime. Yes, they may be good for detection, so should we expect them? And for that, I'm actually gonna take us back to the aquaplanets and take a closer look. Because none of these are actually at geological steady state. For a climate modeler, they're at steady state, but if you look at their budgets, none of these planets are gonna stay as they are. So first of all, our nice, warm, almost entirely melted planet has actually passed the moist greenhouse limit. So what this means is that if you look at its water vapor profile, the dashed line over here, it's nearly vertical. So it's actually pushed a lot of its water vapor into the upper atmosphere, and it would tend to lose a large fraction of that water vapor very quickly. So this planet is not at steady state, it will lose its water. What about our outer two? So their water vapor is not running away, it's in the lower atmosphere, but it has a different problem. And that problem is the fact that the night side is entirely frozen. Let's think about that water budget. Starting with water event rates on the day side, where it's warmer and where you don't have sea ice coverage. So you have your evaporation rates here at the top. Some of that water will precipitate out, particularly in the substellar region. But whatever doesn't precipitate out is going to go into the upper branch of the overturning circulation, and most of it will precipitate out as snow on the night side, which is shown over here. So in terms of a water budget, you have a sink on the day side, you're evaporating water, taking it away, transporting it over to the night side. You're forming sea ice, you're forming glaciers, you're forming solid reservoirs, and your return mechanism is going to be literally glacially slow. You're going to need either ice flow or geothermal melting and really convenient topography in order to have any water returning there. And for our M-dwarf planets, water vapor transport is incredibly efficient. So for a sense of scale, if you took all of Earth's oceans and you let that water vapor transport take over, you would trap all of Earth's water from its oceans in 100,000 years for our Earth-like case, and just shy of 300,000 years for our cooler planet. It's incredibly fast. And so this means that your dayside is just going to be slowly desiccated, and you're going to end up with some huge nightside glacier if you started off with an Earth-like planet. Okay, so point here being, if you formed an ocean-covered world, if you started off with something like Earth, it's not likely to stay that way. So we've run the simulations for the dry extreme. It is not impossible that you would have intermediate cases here. There's a lot to be explored there of what happens once you add some complexity to the system. And so I don't want to overstate that it will become Tatooine. That's not what I'm trying to say here at all. But the point here being that you're probably not going to be able to maintain a global dayside ocean coverage no matter what you do. You can hopefully try to find intermediate regimes. You may find interesting things as we start adding topography and starting to look at these planets with more complex structures. There may be some steady states to be found yet, but we have to be very cautious of assuming how much water, and definitely concerned about whether or not these would be like a global ocean basin network similar to Earth. So if there's one key takeaway for the talk so far is that, particularly for synchronous rotating planets, we're also focusing on the slowly rotating regime here today. TRAPPIST has a couple extra details that I'm not going to get into. But for these planets, the habitable zone is a dangerous place from a climate point of view. You're going to get water vapor escape, and you take a tiny step out and you hit nightside cold trapping. And the turning point there is just whether the nightside is frozen or not. There are other reasons to worry about water on M-dwarfs. I think you're probably very familiar with them, but just to reiterate a few, one being that we expect less water delivery to these planets in terms of impacts. So they might not even form with as much water as Earth does. And there's the early M-dwarf problem that M-dwarfs have a very, very energetic childhood. Their early period is likely to cause significant water loss. And it has a very long childhood compared to our sun-like star. And so again, it's a bit questionable how much water you expect it to have overall. Which bodes well for expecting land planets, or planets with more limited water regimes. Now, I do want to sort of just pause to say that when I say water limited, I don't necessarily mean entirely dry. We tend to overstate, I think, sometimes these loss mechanisms. Fewer impacts doesn't mean zero. There's also a lot to still be thought about in terms of water coming from the mantle and what that timing might entail for these planets. Mantle water might give us a water source that is after the M-dwarf enters the main sequence. And so there are several mechanisms still to be explored as to where the water for these planets might come from and how late it could appear into the system. And so, while I'm very much pushing back on the idea of imagining Earth, we're not necessarily expecting all of them to be completely desiccated. And if they do receive water, there's a good chance that that water will tend to be trapped on the night side. So if you get late impacts, you're still going to be subject to nightside cold trapping. If you get mantle water and this planet cools, it's still going to be subject to nightside cold trapping. And I want to take just a minute to say why that's not actually the end of, that's not as bad as it sounds. And the reason is the terminator is very conveniently located near those glaciers on the night side. And so if we assume that it actually, this planet has gone into nightside cold trapping, it has whatever small water reservoir it originally contained is trapped on the night side, what happens right at the edge of those glaciers? So this is just a back of the envelope point, but I think it's a fun one. In order to accumulate surface water, the rule is you have to have more water coming in than you have going out. Just a basic budget. Water going out, our sink, in this case, is evaporation. And we can put an upper cap on evaporation using the aquaplanet simulations. Aquaplanets love to evaporate. If they can evaporate, they do. And so you can think of it as an upper limit to how much water can be removed from the terminator if there's infinite water available. And so we can take a limit from our Earth-like aquaplanet. You notice the terminator is not the warmest part on the planet, so it doesn't evaporate quite as much as the area closer to the substellar point as this ring. And we can compare that to potential water sources. So let's say we have this glacier on the night side, and it is moving as slowly as it can through ice flow. Now, ice flow is going to be very hard to constrain. It'll probably be a long time before we know that number with precision. It'll depend on the topography, the planet's gravity, the size of the glacier deposits on the night side. We can make an educated guess here just for fun. And think about Earth's glaciers. Think about Antarctica. If we look at the flow rates that we get in Antarctica and we take some of the edge flow rates and we apply them to, let's say, a 10-meter glacier. So nothing too drastic. It's not the multi-kilometer glaciers of Antarctica. But we just take that flow rate and say that, you know, it's Earth's gravity, Earth's flow. We can extrapolate how much water will be coming out into the terminator from a nightside glacier that reaches the edge there. From these two simple scaling arguments, we can actually quite easily have our evaporation be substantially lower, orders of magnitude lower than the ice flow. So this means is that locally you would have sources exceeding sinks. Now, the optimist will tell you, you know, if you're optimistic about the size of the nightside glacier or the flow rates, this could be a river, could be a lake, could be a small ocean. Pessimist version of this is it's soil moisture. You have a little bit of water there that's going to be held in place through evaporative resistance, and you just have a nice fertile piece of soil, potentially fertile piece of soil. And more likely than not, something in between. So the convenient thing is that right at the terminator, in that little region at the edge, we could have quite interesting intermediate regimes taking place. It's not enough if you sort of spread that flow across a significant portion of the dayside. It's not enough to release all the water that was trapped, but it is enough to create regions of surface water. And the end result would again depend on topography as well. So just a fun aside about what we might eventually stumble into with terminator habitability planets. But overall, we do have to be cautious of expecting an Earth-like abundance of water in an M-dwarf habitable zone. And so with this in mind, I'll take the time I have left and shift over to Ks. So it turns out that our M-dwarf systems are a little bit too hostile. Or let's say that we become very keen on finding a planet with more abundant water, something a bit more familiar to us in terms of development of life. K-dwarfs can give us better prospects for ocean-covered worlds. So there's a couple of reasons here. A lot of the things I was talking about before, you get a more stable stellar environment. You're going to get more water delivery. You can also get a lot of different regimes, orbital regimes in the K-dwarf habitable zone. For simplicity, I'll just talk about synchronously rotating for today. But there's a lot more to explore here. What changes? So let's go back to some of those basic dynamics. You're going to get a lot less near infrared radiation with the K. But the overall pattern stays similar. So you're still going from stronger overturning for the cold planet, weaker warm planet. Same basic principles apply. Just note that you're now actually going to much higher radiation levels before you reach your moist greenhouse limit. So the inner edge is receiving a lot more radiation here. And so our Earth-like planet is the second from the right. Looking at sort of similar things we were looking at before, the overturning circulation, it goes through a similar shift from a deep circulation to a shallower one with increasing efficiency. Here, just to highlight, once again, the planet that I'm showing you at the inner edge is the planet that has passed the moist greenhouse limit. And everything inward of it is fine in terms of water vapor loss. Analysis. One fun quirk here is that this planet manages to pass the moist greenhouse limit without melting the night side. So it's a bit of a quirky little edge case there. But we don't worry about it too much because we want to find a stable planet. What about the night side cold trapping, since that was our biggest concern before? You actually get a lot of fun things here looking at snow for K-dwarf synchronous planets. You get this dayside snow ring. It's not dynamically that interesting because it's snow that's falling over the open ocean. It's actually just being caused by turbulence that you get at the sea ice edge, which happens because you get a stronger ice albedo feedback. If you remember way back to the beginning, I said the ice albedo was weak for M-dwarfs, it's a little bit stronger for K. That's how you get this rather odd looking snow profile. But for us, the important part is this night side snowfall. So you'll notice that you have pretty significant values here at the inner edge, but you can see it decreasing quite significantly as we move out. you look at those timescales, you'll actually see it increasing a couple of orders of magnitude as you move further out into the K-dwarf habitable zone. And by the time we get out here, we're looking at that million-year timescale. This would not be difficult to overcome. So if we assume geothermal melt rates comparable to Earth, so a planet that formed similarly to Earth has comparable internal heat sources, you can actually exceed this melt rate by about an order of magnitude. The melt rate will exceed this transport rate by about an order of magnitude. So it wouldn't take a lot for you to establish a strong return flow that exceeds this very mild atmospheric transport. Our Earth-like case is right at the borderline. It would depend if you had, and super Earths could get their way out of this because you'd assume a more geothermal heating. Earth-like case is right on the borderline. If it's less geothermal heating than Earth, it'll be nightside cold trap. So you're right at the edge here. Inward, you'll still be getting nightside cold trapping. So the fun thing here to highlight is just that it changes our picture of what the habitable zone looks like for a synchronously rotating planet. So while for the M-dwarf, we get that switch from dayside, from water vapor escape to nightside cold trapping, for the K-dwarfs, it really highlights that nightside cold trapping is an inner habitable zone feature. And so for some of these systems, we might be able to find regimes that are beyond it. You would also have additional regimes that would allow you to retain oceans overall, but even for asynchronously rotating planets, we have more reason to hope for liquid water oceans that are covering a greater fraction of the planet, as well as more delivery of water and more Earth-like formation configurations. So if you're keen to find abundant water, whether it's to study ocean dynamics or whether it's just for similarities to Earth in terms of biosignatures you'd hope to find, our K-dwarfs will probably be a good bet and something we can hope for with HWO. But for M-dwarf planets, we should be prepared for drier planets overall. But that doesn't necessarily mean the end of the story. Hopefully we can still find a lot of interesting results thinking about drier planets. It also does have implications in terms of observing strategies, with your K-dwarfs potentially having greater cloud coverage if they do end up having greater water abundance, whereas our M-dwarfs may turn out to not have to worry quite as much about water vapor as cloud coverage as we might have previously thought with aquaplanet simulations. So with that, I will just leave up our reminder of key conclusions in terms of abundance, potential abundance of drier planets around M-dwarfs, the resulting larger gradients in temperature that you will get, allowing you to have fun things like planets in a terminator habitability configuration instead of your eyeball climate, and the potential benefits and challenges associated with. Advantages outweigh the negatives in terms of what we might be able to do in the coming decade. And then finally, our fun K-dwarf initial results that it will offer us better prospects if we're hoping to find a planet that looks more similar to Earth. So with that, I'll stop and take questions.